Hello students, we are going to discuss problem on module 4, that is the radiation chapter here based on the radiation shield. So usually in the examination this kind of problem they may ask for the shield to calculate percentage reduction. Okay, I'll read out the question. Consider two large parallel plates, one at 1000 Kelvin with emissivity of 0.8 and other is at 300 Kelvin having emissivity of 0.6. A radiation shield is placed between them. The shield has emissivity as 0.1 on the side facing hot plate and 0.3 on the shield facing cold plate. Calculate the percentage reduction in radiation heat transfer as the result of radiation shield. Okay. Then initially there are two hot and cold plates are there. So they are introducing one shield having one side hot place facing towards hot plate, that is the emissivity is given, that is 0.1. Another one is facing towards cold plate and their emissivity is 0.3. So if it is the case, what will be the percentage reduction or radiation reduction in radiation transfer as a result of radiation shield? With the shield they are asking. So let us write what are the given data first. First you write the data and analyze the problem. So there are sheet like this on the hot plate, another one is cold plate. Assume this is hot, it's a hot plate, this is cold plate, hot and cold. Okay, so in next case what they will do, for the same plate they are introducing one radiation shield. So this emissivity, emissivity1 and emissivity2 we call emissivity2, but when they are introducing the emissivity of the third plate between them, so it becomes epsilon 3H epsilon 3C we can say. Okay, because cold side and hot side we have to identify, that's why we write it as hot and cold. This is what we can say radiation shield. Okay, now write the data. First it is given, that is temperature T1 is equal to 1000 Kelvin and emissivity is given 0.8, emissivity 2 is given for, that is 0.6, and its temperature, that is T2 temperature, is given 300 Kelvin. Okay, so emissivity 2 at the 3 at the hot side is given 0.1 and emissivity 3 at the cold side is given 0.3. Okay, now we can write first one, we call the figure A and figure B. Okay, for the A, the heat transfer per meter square area, the heat transfer per meter square area between two parallel plates, parallel plate is given by plates by radiation is given by Q is equals to sigma T1 to the power of minus 4 to the power of 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. So now you have to substitute the values. 5.67 10 to the power of 4, 3 to the power of 4. Okay, 1.25 plus 1.67 minus 1. You may ask how we got this. So I'll tell you example. Suppose this is 5.67 this value. Okay, and you have to write Kelvin you have to write it, the denominator you have to 100 minus 300 by 100 to the power 4 divided by 1 upon 0.8 plus 1 upon 0.6 minus 1, we'll get this value. Okay, after solving this, we'll get Q is equal to 29292 watt per meter square or 29.29 kilowatt per meter square. So this is the heat transfer between the two plates without shield. Now we are going to calculate when you keep the shield in between them, what will be the radiation, that you have to find out. So case B, what it is, when the two plates are there, you have to introduce one more shield here in between them. So with shield, what is the heat transfer? So Q is equal to summation T1 to the power of 4 T2 to the power of 4 divided by 1 upon epsilon 1 plus 1 upon epsilon 3h minus 1. Okay, the Q dash so is equals to epsilon T1 to the power of T3 to the power of 4 minus T2 to the power of 4 divided by 1 upon epsilon 2 or epsilon 3c plus 1 upon epsilon 2 minus 1. So this is the radiation shield kept between the two plates. Then the thermal equilibrium, this is thermal equilibrium, can write. So here what happened, the temperature T3 is of shield is 3 epsilon 3h and T are emissivity of the shield towards hot plate surface and that cold plate surface. Substituting given values in the equation, then substitute the value, that is 1000 by 100 whole to the power of 4, because this and this will get cancelled, minus T3 by 100, this will be 3. Okay, whole to the power of 4 divided by 1 upon 0.8 plus 1 upon 0.1 minus 1 is equal to T by 100 whole to the power of 4 minus 300 by 100 to the power of 4 divided by 1 upon 0.3 plus 1 upon 0.6 minus 1. Now we can write 10 to the power of 4 to take this value as x, where x is equal to T3 by 100 you consider, so and simplify, and 1.25 plus 10 minus 1 is equals to x to the power of 4 plus T3 to the power of 4, 3.33 plus 1.67 plus minus 1. Okay, now divided by 10.25 is equal to x to the power of 4 minus 81 divided by 4. So now we can write 1000 x to the power of 4 is equal to 10.25 by 4 x to the power of 4. Okay, x to the power of 4 minus 81 is equal to 2.56 to the power of 4, 207.36. Or can write 3.56 x to the power of 4, 10207.36. X is equals to T3 to the power of 100, 10207.36, 3.56, 1/4, so 7.36. 7.32. T3 is equal to 732 point Kelvin. Okay, temperature we got it. Now the heat flow per meter square area when shield is located, then this is T1 to the power 4, T3 to the power 4, 1 upon epsilon 1 plus 1 upon epsilon 3h minus 1. So 5.67 thousand 100 732 divided by 100, 1 upon 0.8 plus 1 upon 0.1 minus 1. So it becomes 5.67 10 to the power 4, 7.32 to the power 4 divided by 1.25 plus 10 minus 1. Okay, so this becomes 3943.5 watt per meter square, or 3.94 kilo watt per meter square, that is Q dash. Okay, once if we got this value, now we have to calculate what is the percentage reduction in heat flow, that is Q minus Q dash, Q into 100. So 29.29, 3.94 divided by 29.29 is equal to 86.54, 86.54 percentage. So this is the answer for percentage of reduction. Thank you guys. Thanks for watching this video. I hope you understand this video.